Hello and welcome back. So we're starting a new unit today on hypothesis testing. And yeah, I know, we just did a whole unit on hypothesis testing, but the last unit was on one sample hypotheses. This unit is on two sample hypotheses. So much the same, but a little different too. Here we go. One sample hypothesis testing tests a claim about the value of a population. That's the unit we just finished. Two sample hypothesis testing compares the parameters from two different populations. Now, before we jump into how this works, first we need to make the distinction between dependent and independent samples. Two samples are independent if the sample selected from one population is not related to the sample selected from the second population. Two samples are dependent if each member of one sample corresponds to a member of the other sample. Dependent samples are also called paired samples. Let's practice and see if we can figure out which one is which. Let's say we have sample 1, the resting heart rate of the PCHS administration before drinking coffee, and sample 2, the resting heart rates of PCHS administration after 2 fire drills. What do you think? Those would be dependent. It's the same people that are being tested. How about this one? Test scores for 15 Blue 1 statistics students. Sample 2, the test scores for 15 Blue 4 statistics students. Those would be independent. One is not related to the other. Sample 1, the height of 35 Pine Creek senior females, and sample 2, the height of 35 Pine Creek senior males. Dependent or independent? Those are also independent. So now let's look at how the two sample hypotheses work. When we perform a two-sample hypothesis test using independent samples, we're testing a claim concerning the difference between the parameters of the populations, not the value of the parameters themselves. So that's a little bit different than the one-sample hypothesis test. The setup of the hypotheses looks very similar. We have a left-tailed test, a two-tailed test, and a right-tailed test. The formula for testing two means is very similar to one mean. In a one-sample test, the formula looked like this. In a two-sample test, the formula looks like this. Just glance back and forth between those two formulas for a second and see if you can see some similarities. So for the one-sample test, it's the sample mean minus the population mean on top. For the two-sample test, we're just getting the differences between the two samples. The denominator of the one-sample test is sigma divided by the square root of n. The denominator of the two-sample test, yeesh, what does that mean? We actually need another formula to figure out the denominator, and it looks like this. Basically, this formula is sort of a combination of the two population standard deviations. Couple things to note. When the samples are large, you can use the sample standard deviations in place of the population standard deviations. If the samples are not large, but you still know the population standard deviations, you can still use the z-test. And that should sound similar to confidence intervals and one sample hypothesis testing. So let's try this out with an example. American Finance Education Company claims that there's a difference in the mean credit card debt of males and females in the United States. The results of a random survey of 200 people from each group is shown. The two samples are independent. Do the results support AFEC's claim? We're going to use critical values and a significance level of 0.05. The null hypothesis in this case is that the population means are the same. The alternate is that they're not the same. We've got a 0.05 significance level, Z distribution, two-tailed test. Now, just like we did with one sample hypothesis testing, we're going to use our cheat sheet that we created to find the correct critical value. We've got alpha equals 0.05 and a two-tailed test. So our critical value is plus or minus 1.96, and we can put that into our decision rule the same way we did for the one sample hypothesis test. If z is less than negative 1.96 or z is greater than 1.96, we'll reject the null. However, if z is between positive and negative 1.96, we'll fail to reject the null. Now we'll start doing our calculations with the denominator of our formula. So under the square root sign, we've got the standard deviation of the females squared divided by the sample size plus the standard deviation of the males squared divided by the sample size. Add them together, take the square root, and we get 77.5. That is now the denominator of our main formula. And the top is just the difference of 2290, the mean of the females, minus 2370, the mean of the males. Put all that into your calculator and we get a z-value of negative 1.03. Since negative 1.03 is between negative 1.96 and positive 1.96, we'll fail to reject the null. If we fail to reject the null, that means we're accepting the null, which means it's likely that there is no difference in the amount of credit card debt between males and females. Let's try another one. The New Mexico Visitors Committee has published that the vacationer's average daily cost for meals and lodging in New Mexico is less than the same average cost for those vacationing in Arizona. The results of a random survey are shown to the right. The two samples are independent at alpha equals 0.01. Is there enough evidence to support the publication of the Visitors Committee? Use critical values. So step one, of course, is our hypotheses. The null is that the average in New Mexico is greater than or equal to the average in Arizona. And the alternate is that the cost in New Mexico is less than the cost in Arizona. 0.01 significance level, we're doing a z-distribution left-tailed test. If z is less than negative 2.33, that's our critical value, we'll reject the null. If z is greater than or equal to negative 2.33, we'll fail to reject the null. And again, we'll start with the denominator of our formula. 15 squared, that's the standard deviation in New Mexico, divided by 50 plus 22 squared, standard deviation of Arizona, divided by 35, the sample size of Arizona. Put all this into your calculator, we get 4.28, which becomes the denominator of our main formula. Now we take the difference in the means, 248 from New Mexico minus 252 from Arizona. Plug all that into your calculator and we get a z-score of negative 9.35. And since negative 9.35 is greater than negative 2.33, we'll fail to reject the null. So therefore, it's likely that the cost in New Mexico is not less than the cost in Arizona. So there's a lot of similarities, right, between hypothesis testing for two samples and hypothesis testing for one sample. Just opens up a whole new world of possibilities on what kind of things we could test. Thanks for being here.